dimensionality reduction, pros and cons. Okay, so pros of dimensionality reduction: removes correlated features, improves model efficiency, reduces overfitting, improves visualization. And you can see that in the graph there with PCA. Without PCA, we're showing accuracy of 0.7467 and 0.74 with the PCA. So, oh wait, I think I had that backwards. So the pro, yeah, so with the PCA, you're not getting as much accuracy, but it's much faster. And so, there's a little small drop off, but you know, you can store most of the data, and you can do visualizations, and with just a small drop off in accuracy. Let's move on to the next slide. Oh, and then there is I did show there that as the features increase, you can see in that bottom graph, as the number of features increases, you get very little pickup in or you know, as the number of features increases, the performance gets better, but as you add more and more features, it gets worse. So, oh, there we go. Okay. Chapter 8 talked quite a bit about, or wrote about, cursive dimensionality. Can you guys hear me okay? It's like really raining right now.
Yeah, we can hear you.
Yeah, your audio is actually quite good.
Okay, okay.
And we're jealous of the rain.
Yes. Okay. Cursive dimensionality. Okay, so I actually looked this up on a copy move forgery project. The link is there on my PowerPoint, and so this was actually studying. I don't know the exact term for it, but it was pictures that were being forged by copying pixels or data and moving it to a different spot on that image. And so they studied on ways to detect that, and using dimension reduction. And so let me get to that chart. Some of the advantages: small variations due to noise and lossy compression can be detected accurately. Less computation complexity and robust against post-processing operations. Forgeries with additive noise and JPEG compression can be detected. And those are all different types of dimensionality reduction. And then, but some of the disadvantages for low quality images: as size of block decreased, so does the efficiency, cannot deal with JPEG compression. So that was some of the issues that they had running dimensionality reduction on that type of a project. I don't know, have any of you ever tried to use dimensionality reduction with image data sets? No?
Not necessarily specifically with images. I think we can, I'm not sure how many slides you have, but I think this chapter is not too heavy, so we can afford to kind of like pause and, you know, talk about some of these things. So yeah, it seems to me that, you know, in the older days when we had statistical models like linear regression, logistic regression, you know, you do run into some issues with overfitting with additional features, and you have some numerical issues when you have like columns that are sort of collinear and that sort of a thing. I personally feel like, I'd be interested in other people's opinions. I feel like with today's algorithms, things like gradient boosting, neural networks, they're not as sensitive to having additional inputs. They can just sort of ignore the extra inputs. As opposed to like linear regression, yes, there's ways you can do like lasso regression or whatever, but out of the box, it doesn't ever ignore your inputs. And so it's really less of an issue. There are definitely some performance concerns if you have 10,000 features. Maybe it'll run a lot faster if you say, well, 1,000 features or even 300 features explains 99% of the variance, right? But I feel like today I would never blindly do dimensionality reduction. I would at least try to run it on the full thing, and then maybe I would do dimensionality reduction and see if I get similar performance. And if so, then I can do a lot of experimentation faster with the reduced features. But I would always feel compelled to at least try it with the full, just at the end of the day, to make sure that wasn't hurting me.
We had a project where we were using, and this was a Kaggle project, so some of you may be familiar with it. It was a Expedia client customer clustering type of project, and it really didn't. There were quite a few data. The data file was pretty big, but it didn't really change anything when I split the data set, and it didn't really. There wasn't any kind of advantage in speed, or for me at least, with that type of a project.
So I go back to what we do in driverless a whole bunch, but that's just because I've seen that the most. One of the things that we do inside of driverless is when we have text input, we'll do a count vectorizer or TF-IDF vectorizer. And that's something that you very commonly do some sort of dimensionality reduction on, because you have a new column for every single vocabulary word that you have. And so that can be 20,000, 30,000, 50,000, just depending on the size of the data and the diverse vocabulary that you can have. And so you can end up with this massive set of tens of thousands of columns. And then one of the common things that we do is some form of dimensionality reduction on that. And it does actually speed it up a lot. And very often there's hardly any performance difference. Sometimes it's actually better. But there's kind of two different things that you're trading off there potentially. So imagine there's kind of two ways that you can limit that. So the count vectorizer, it takes in the text and then it creates a new column for every single different unique word that you have, your whole vocabulary. And so you can cap the size of your vocabulary. That's one way to limit the dimensions. So you can say just only take the 10,000 most common words or something like that. Or you can take all of the vocabulary and then you can run dimensionality reduction on it. And I think in general, you would find that taking the entire vocabulary and then doing dimensionality reduction is going to end up a better result than just capping the vocabulary in some way.
Yeah, I'm curious with the text analysis, because we kind of did the same thing with that Marriott or the Expedia project. We had, I believe it was 37 million data points, and we dropped it to like 70,000. We just took the sample of 70,000. But do you typically have that type of a drop off, like we saw in this chart here, from accuracy of 75 to 74?
Yeah, I would say that's probably pretty typical, honestly. You have to give up some information. It's not necessarily for free. Like if you have 10,000 columns and you reduce it down to 300, you can probably get pretty close to capturing all of the information, but not completely. So you are giving something up. But if you're going from 10,000 down to 300, it also makes it a much simpler and faster model.
Hey, Harold, we do have a question in the chat, but before we get to that, I thought I would just sort of mention, so we haven't really gone in much. Talking about what PCA itself is, I don't know if most people are familiar, but it's a linear process. You hear about it a little bit in linear algebra class, and so basically it's finding a rotation, so to speak, of your dimensions, such that the x-axis, the very first dimension, is the one that has the maximum variance. And then the y-axis, your second dimension, will have the second most variance, and then so on and so forth. It doesn't really make much intuitive sense past 3 dimensions. It's hard for us to talk about it, but basically they're all orthogonal dimensions. And so you can think of it just simply as rotating the dimensions. So it's lining up your data so that the maximum variance is right directly along the x-axis. And if you do this, then what you can do is, instead of using all the dimensions, so let's say you start out with 10,000 columns, you can say, I'm just going to pick the first however many. And in sort of sorting the dimensions that way, then of course you're picking the ones that preserve the maximum amount of variance. The thing I always say when we talk about PCA is variance in the total data does not necessarily equate to the variance you care about. Okay, so I've given an example before where imagine you have a chart and it's like basketball players, and you have height and you have reflexes. So somebody's reflexes may be very directly related to how tall they are. Generally speaking, the taller you are, the slower your reflexes are, right? But you're not interested in that primary relationship. What you're interested in is the people who are, the unicorns who, despite being tall, have slightly better reflexes than the average 7-footer. And then the people who, despite being 6'6", have better than average reflexes, and so on and so forth. And so that's actually not the main direction of variance. The main direction of variance is just this strong signal that says the taller you are, the worse your reflexes. So if you did PCA on that, then you potentially are losing the very information that you need in order to predict who's going to be a good basketball player.
Great. And yeah, I think that says it pretty good. Let me see if I can find it. Get us moving along here. Okay. And Ryan, did you address that question, features engineering, come into this field with that link that you sent, or should we talk a little bit about that?
No, that's slightly separate.
Separate. Okay.
Yeah.
Yeah. Features engineering come into this field? Is the question. Yeah, I mean that is also a type of dimensionality reduction, I would say. I'd be open to discuss, but yeah, I mean, I don't know technically if it would be called features engineering, but the whole point is, getting rid of the noise and, finding a quick and easy way to make predictions. And so I think features engineering is one way to do that, as is dimensionality reduction.
Yeah, for model accuracy, again, gradient boosting machines, neural networks, those types of algorithms, they're not really going to care if you have multiple collinear features in terms of model accuracy. Having multiple collinear features does, however, hurt your interpretability of the model, because the models potentially spread sort of the influence across, multiple features. So there are potential benefits to getting rid of multiple things that are just all saying the same thing, and then in terms of like, if you're engineering completely new features, like the ratio of column 1 to column 5 and things like that, then you're actually adding back columns, but that's because you're trying to give the model data that's actually much easier for it to work with, much more expressive for ultimately what it is that you want to predict. So yeah, I think Ryan gave a really good example, especially you have sparse data like the TF-IDF features, then dimensionality reduction is potentially a very helpful feature engineering step. But as I was saying, I don't have that much experience with it, but I just don't really see a lot of value for dense data.
You know, I taught in linguistics once, and it was very interesting experience, in particular with the language analyzing. And at some point, they were considering pipelines for cross-validation. And it's turned out that, well, with count vectorizer, you can reduce not only the most rare words, you can reduce the most frequent words as well, so-called text-specific stop words. And it turned out that half of the most frequent words wasn't used for classification. That was rather interesting.
Yeah.
No result. Well, it dropped some of the rare words as well, but I've never seen that people would remove half of the most frequent words. Also, you know, if to think about if you normalize everything, then these are the words which will have smallest variation, because everything will be divided by the frequency. Oh, well.
Yeah.
One
Go ahead.
one of the projects that I'm working on right now, just talking about the interpretability side of things, I'm working with Citibank, and they are looking at transcripts of some of their customer calls, and they're trying to classify them as complaints, not complaints. And our first iteration was give them TF-IDF of this, and then we do dimensionality reduction on it. And they weren't very happy with that, because you look at the variable importance and it's like, what the heck does text dimension 32 mean? Because it doesn't correlate to any specific vocabulary necessarily, because it's this weird linear transformation that's been done on top of it. And so then what we did is we swapped to just TF-IDF, and we said, okay, no dimensionality reduction. Now we can show you your vocabulary. But then the problem was what Maya was saying is basically the feature importance we're showing that like the most important word was like this and me and stuff like that they didn't think were particularly interesting. So then we did some techniques. We removed stop words and various other things in order to limit it to words that they thought were actually interesting. And then we finally got it to pop out like words like supervisor and manager and frustrated and stuff like that. So just in terms of interpretability, the dimensionality reduction kind of hurt us in that regard, because you can map it back to the vocabulary, but it's not necessarily the simplest thing.
Yeah.
I think just to think about like the question that was posted in the chat. So like dimensionality reduction falls underneath the broad category of like data reduction. And there's like a dozen different ways you would reduce your data set. And so like if you're starting your model, I think most people start off like there's going to be irrelevant features automatically that you know you're not going to include. Maybe it's like the ID or some kind of descriptive variable that you're not going to use. So that would be considered attribute subset selection. And those are the attributes you automatically know you're not going to use at all. And then what Ted was talking about, where you may take a ratio of 2 columns to create one, that's called derived variable creation. And so a great example of that is sometimes you have variables that are not, have no association with the target feature until they're combined together. So a great example is like BMI index in terms of predicting whether or not someone has diabetes. So BMI is a ratio of weight and height. If you were to just take like height, for example, a person's height doesn't correlate to or is not associated with predicting whether or not they have diabetes. But when you combine weight and height together to get the BMI index, now that new feature, which is like your derived variable, now that does have an association with diabetes. So that's one technique you can use. But when it comes to like feature reduction, there's like two types of methodologies that you can go by. Like there's methodologies that leverage the target feature as a factor as it's deciding what's the most important. And you'll find that in like your ensemble models and your decision trees. But then you have PCA, which doesn't leverage the target feature, but just pretty much looks at the correlations within the data set as a whole. So what I found when I use PCA, I do other data reduction techniques first. The first thing I do is I eliminate any features that are not relevant to my target variable. Because I mean, I don't care about it, because otherwise PCA, because you can have a lot of features that are correlated, but not correlated to the outcome you're trying to predict. So I eliminate those features first. And then of course I do maybe the attribute subset selection. I get rid of the features I'm not interested in. And then if I still have lots of features that I want to reduce, then I would do PCA at that point.
And I've got my project handy if that's something people want to look at, where I had from 24 column to 150 column numbers, where I just took those aside and ran the PCA on just those columns. And like Ryan said, it was, they're labeled as, D1, D2, D3. So it be looking at them, but if we want to take a look at that, and so back to the chapter. So two main approaches for dimensionality reduction: projection. This approach works well when many features are almost constant, and manifold learning, which is one I had a little trouble with. Projection, that's the one that most people use. It's the most popular. It's the PCA, principal component analysis. That graph there is related to manifold learning. But let's talk about PCA first. There's randomized PCA, incremental PCA, kernel PCA. These are all hyperparameters that you can use to tune the model, make it faster if need be. Kernel PCA, that is the graph below. That one I am not very familiar with, but allows you to perform nonlinear projections. Has anyone ever used kernel PCA? No.
I haven't, but in terms of this chapter, that's the transition from the projection, the straight vanilla PCA is a linear projection, okay? And then once you start doing kernel PCA and other algorithms, then you're talking about something which ideally might be more powerful because it can do nonlinear things, but it's not guaranteed to work.
Yeah, so yeah, linear, nonlinear. These are the nonlinear, and the linear different techniques for dimensionality reduction, as we were talking about. So I think I labeled them here. Locally linear embedding, or LLE, is, I don't know why they throw that linear name in the title, because I believe it's a nonlinear type of manifold learning method. Random projections, that's linear. Multidimensional scaling is a linear method that transforms the given matrix into a low dimensional matrix based on the distance of each element. Yeah, so here are the different types of techniques. Most people use the principal component analysis. There's also the T-distributed stochastic neighbor embedding, and then LDA is a linear technique similar to ANOVA. But that one I had a little trouble with, where it's using the, what is it? Builds feature combinations based on differences rather than similarities. I was up last night doing this PowerPoint. Yeah, so it instead of looking at the at the distance from 2 points, I believe it looks at the distance. There's a different type of distance that it looks at, LDA, but I'm not familiar with the nonlinear techniques. But if we want to, I can bring up my, I don't know how much time we have left, but I can bring up my project. We can take a look at how this is done using Scikit-Learn.
Okay, yeah, why don't you pull it up?
Okay, yeah, I'll do that. If anyone, let's look at the, there was a question in chat. When the dimensions are reduced, the features are reduced. Is it only the number of features reduced, or as well as the feature itself?
Yeah, so PCA is doing more than just simply picking a subset of the features, right? So if you start out with 100 and you pick 30, those 30 are linear combinations. So it could be 50% of column 1, 5% of column 13, 7% of column 21. And so you're not just simply dropping features. I don't know if that answers that question. Interesting.
Okay, can everyone see my project here? So I just kind of skipped ahead to the part where I reduced the features, but I can backtrack a little bit. This, like I said, this was a Expedia project where we were clustering the customers according to.
I'm still seeing your PowerPoint.
Oh, okay.
Hi, may I ask a small clarificatory question, please? Hello?
I'm sorry?
Can I ask a small clarification? So,
Sure.
I'm just trying to understand the basics. So if I understand correctly, the objective of PCA is to reduce the dimensions and see which axis have the highest variance, right? But in the example that Ryan mentioned, this TDIDF, and that's kind of topic modeling. That's a supervised machine learning for prediction, right? To classify. So here we are not classifying, or we are not predicting anything, right? We are just seeing the dimensions.
So what Ryan was saying is, after you do your TF-IDF, you end up with one column, one feature for every word in your vocabulary. If you don't want to use all of those in the model building phase, what you can then do is you can run PCA on, let's say, those 20,000 columns and squish it down dramatically to, say, 300. So then those 300 might capture, for example, hypothetically, the word upset, mad, whatever, pissed, might all kind of map to dimension 1. And thank you and whatever, might map to dimension 2. And, so instead of having to have every single word be a separate column, you just say, here are my 300, most, again, it's an unsupervised technique, but so in terms of using variance as your guide, your hopefully most interesting dimensions out of the data.
I'm trying to, sorry.
I just wanted to jump in and clarify one thing. So TF-IDF is just a process of transforming the text to a big matrix. It's not necessarily doing anything with supervised learning yet. It's just a transformation of the text to this big matrix. And then you can do dimensionality reduction, or you can pass that to graded boosted decision trees or linear regression or whatever you want. But the TF-IDF itself is not actually classification or anything like that. It's just a transformation from text to a matrix.
I see. Thank you. Thank you.
Yeah, and then this question here, if I'm reading it correctly, so it sounds like from the question that you want to know if there will be new features that will come out of this PCA analysis. But from my understanding, it's just going to find the ones that that affect your variables the most. So actually, I've got a pretty, let me refer to my project. It might help things a little bit. So I'll just back up. It's pretty short. So you're importing your PCA from Scikit-Learn, and then you're reading your data. This was, like I said, around 37 million data points that we just lopped off to 48,000 for this project. And then what
Hey,
we did
Harold,
was,
so most interestingly, can you just tell us how many columns you had in the data? I mean, the fact that it's a subset of your data, whatever, you know, but I think the interesting thing will be how many columns you have in this rectangular data set.
Yeah. So here we got it. It was 173 columns, and that was total. So and let me show you some of them. So you can see here, you know, continent, country, region, but at the very end, we get D140, D141, D142. And so that was after we took some additional data and merged it. And then, so let's see, so 173 features. And what we did here, okay, that's just some conversion of the date time. And then, so here is where we reduce the features using PCA. Once we did that, we did this graph here showing the variance ratio. Let's see the x-axis. Okay, so 57 points or components, and we just looking at the explained variance, we I believe we stopped it at 10, which got us to almost 81% of the explained variance.
Why does it go into like two directions? I guess like what?
Oh,
why is it like a blue and red component?
Yeah, the red. Let's see.
Or is it
So
like a sum?
Yeah,
it's like
so
they both add up to. I see.
Mm-hmm. So the red is that specific component explains it 37%, and then the blue is showing as you add those up, it cumulatively goes to 100. Yeah, but each additional component is adding less and less because they're sorted by the most explained variance.
And I've got another chart that will look a little bit more familiar.
I don't know if there's a common rule of thumb. I mean, I think 80 is maybe a little bit on the lowish side. I don't know if people would typically shoot for, you know, something in the 90s in terms of not wanting to lose too much. And obviously you can try, you know, slightly more, slightly fewer PCA principal components.
Yeah. Let's see, what would we use? These are the hyperparameters. This was a while ago we did this.
So while you're pulling that up, there was a question in the chat a little earlier about the code on page 221. So that was Sule. I apologize if I'm not pronouncing your name right. And one of the things that Aurélien does in this book that's good is he shows you how to run all the things that he's talking about in Scikit-Learn. One of the things that I find a little bit sometimes confusing or overkill is that he will point out that there's actually multiple ways you can accomplish the exact same thing in Scikit-Learn. And so sometimes it's like, oh, well, there's this particular linear algebra library that will do it for you, but there's also this other place where you can do it, and then there's this modeling place where you can do it, and so it gets a little bit confusing with the different options. But in this case, I don't know what the specific question is, but basically, we've got data in a big NumPy array. The first thing we do is we center it. So we subtract from every value the mean for that column. And so that then makes it centered on 0. They're not doing anything to change the spread in terms of the standard deviation, right? They run the SVD. So this is the singular value decomposition from the linear algebra library. So I believe in the book, he talks about how SVD is one of the ways you can calculate the principal components. There are different algorithms people have figured out that will end up calculating the exact same thing. And then basically you can see they then say this new result, this VT, has as many features as the original thing, and they're just pulling the first two. So first they pull effectively column 0, then they pull column 1. So those are the first two principal components. I don't know if that answers your question.
Yes, it does.
Feel free.
Thank you.
Okay, thanks.
Yeah. So, yeah. Does anyone go ahead?
The other thing I would note is that most of these PCA systems return them in decreasing order of importance, if you want to call it that. So, you can say, oh, just truncate the first 10 or something like that very easily, right? In Python, just colon 10, right? Or something like that. And I think that's one of the reasons they did it, because it gets very easy to manipulate then when you're coding it in Python.
Yeah. Yeah, and so you can see here from this project, we started out at 173, or actually, and then we applied the PCA to 149 of those 173, and got it down to 34 features. And so here we show the 34 biggest ones, and they've got this new, some of them have the titles that are descriptive, some of them don't. And then we ran, just looked at the correlations, did a heat map, and then we split the training set and test sets. And then we ran, using this data, we ran a random forest and a decision tree. And at the end, neither of them were very predictive, but here's the random forest, and accuracy score we got was almost 12%, but that was on the random forest. And then, oh, I'm sorry, random forest is 0.2583. So, and I can back up if anyone else has questions about earlier work in the project. But does anyone have any questions or want to talk about some other chapters or some other parts of the chapter that I missed? I can pull it up.
Well, I think I just want to make a comment, because I know reading the chapter, there's a lot of mathematics and there are like components that I don't think are really explained as well. So like the way that I would explain like PCA is kind of, when you have high dimensional data sets, it's a high probability that a lot of your features might be correlated. And so PCA is going to take all of those features and then reduce the dimension down and create new synthetic features called principal components. And one of the ways that it starts off is that first PCA is going to identify a hyperplane that lies closest to the data. And so the most correlated features get sandwiched into each principal component. So the first principal component that you see contains it's a set of those features that are correlated. So you can kind of think of it like each principal component is like a big equation that sums all the coefficients times the input values. And then the second principal component, each principal component afterwards, when they say they're I'm sorry, now I'm getting my words tongue every time I talk about this. When they say they're orthogonal, that means that they're not correlated. So each component has the features that are correlated with each other, and that's separate. So when you get to smaller features, now you have smaller features that are the components that are not correlated with each other. And so that kind of helps me kind of understand a little bit better. But this book doesn't talk about like eigenvalues. It doesn't talk about like scree plots. And that's kind of how I learned PCA, which kind of helps me visualize that better. So I wish that the book like showed those other facets of the model, but it doesn't.
Are those and those are used with the linear method, the eigenvalues?
Yeah, so like a lot of times if I wanted to see like the amount of variation that each component has, I'd run a scree plot. Or if I wanted to select, okay, what is the optimal number of components that gets me to like 90% or 95% of the variation, I can see that with a scree plot, or I can run you know, a function to kind of assess how many components are there. But I wish that, but the book doesn't show that. So I've seen other statistical books or machine learning books that really show you how to create the scree plot, and that I think it makes it a little bit better to understand the concept when you can visualize that.
Well, and Harold, I mean, you showed us the plot. The blue line shows, right, as you add various ones, how close do you get to 100% of the total variance? So at 10 principal components, you got to 80%. And if we wanted to get to 90, if we want to get to 95, we could look at that and we could easily read off, you know, whatever, I don't remember exactly what it looked like, but if you need you know, 16 to get to 90%, if you need whatever, you know, 20 to get to 95% of the explained variance, whatever.
Yeah, and if you choose to follow with like your model afterwards, then you would just leverage the principal components as your new features instead of the original features in your data set. And so, and then PCA in statistics, we can also use the components to then do factor analysis, which finds like the underlying factors within like survey data. So it's a great technique in statistics and machine learning to kind of understand your features and the reduction of your features as well.
Yeah, I think that's a good point. You know, I was earlier speaking more about sort of non-parametric methods. And so, you know, when you're dealing with gradient boosting and neural networks, we tend to not really care about PCA and things like that. But if you're doing something that's more on the statistical side, or if you're actually trying to do, you know, inference of causality, then, you know, factor analysis, PCA, these are things that may be much more in your toolbox.
So if no one has any other questions, I think I need to. Are we done at 2 with the presentation, or 2 o'clock?
So 1:30. So we have half an hour. So we're 2/3 of the way through our time. So let me throw out a discussion item. So we've talked a lot about PCA, which is a linear method. It's technically a projection. So we're doing a linear projection onto new axes. So what I talked about earlier about technically you're sort of rotating it to picking a new x-axis, that sort of a thing. I've seen the local linear embedding LLE. I've seen t-SNE used quite a bit in terms of the non-linear techniques. I've seen them used a lot for visualization. So if you're doing some project and you've got data that's high dimensional and you just kind of want to visualize like, what is my algorithm doing, then you might try to visualize the top 2, in some cases the top 3 dimensions. I find even 3D charts hard to read, so often 2 dimensions. You can do linear PCA, you can just take the first 2 principal components. That often isn't that helpful because the data isn't necessarily linear. It might follow some sort of curve in multiple dimensions. And so that's where they talk about the manifold learning. So I've seen, like I said, I've seen LLE and t-SNE a lot in terms of, hey, how I'm going to visualize my data. I'm curious if anybody here has a comment in terms of, have they used these nonlinear techniques for actual like featurizing, you know, for dimensionality reduction or something, other than just for making visualizations?
So one of the ones that I use reasonably often is called UMAP, which is a separate one. But there's certain issues with some of the algorithms, like with t-SNE, you can't actually rerun the same algorithm on new data. You're not doing something where you can fit to your training set and then apply to your validation set. Because of the way it works, you have to fit it to all data at once, basically. Applying it to new data is somewhat meaningless. I don't know the deep details behind that, but I just know that if you look at like within Scikit-Learn, there's only a fit transform. There is no separate fit and then transform because of that reason. So you can't really use it for futurization because it inherently does both at the same time.
In the textbook, it talks about the Swiss roll, which is that non-linear. Is that typical? I tried to do some searching on or Googling to see, if that was a real life issue. Is this? Do you get that type of a data set with text data, like a
That's kind of just a synthetic example, just to show like what are the different properties of the different dimensionality reduction tricks, because some of them can actually kind of undo that Swiss roll and others can't. They're going to just chop it across various different planes and then it'll flatten it out, but it doesn't really capture all of the information. But you're just kind of trading off what assumptions you're making about the data when you're doing that unrolling. But the actual Swiss roll data, you're pretty much never going to see anything like that.
I guess going back to like the question about like using like the non-linearly dimensionally reduced feature space as like an input to like some method. I guess like one thing, I don't know. This is also sort of like a visualization thing, but one thing I have seen with UMAP is I have seen people like run UMAP to cluster it down, like data it down into like 2 UMAP dimensions, and then cluster, whatever, dimensionally reduce it down into the UMAP dimensions, and then cluster in the UMAP space. So that's one thing I've seen, but I feel like that's also mostly just for like visualization, because you could like, because like, I don't know what the easiest way to explain this is, but I guess like with like t-SNE and UMAP, these are kind of like methods based on like this like nearest neighbors graph, which is kind of why they're able to, I guess, learn or capture this like nonlinear variance. So there are ways to just like cluster on like the graph itself and not use like like UMAP or t-SNE dimensions, but I think usually that produces a result that's, I guess, less clean when you view it in like the dimensionally reduced space. So I guess like one way to clean it up is to just cluster after you do like the dimensionality reduction.
And is that using the UMAP to do that? Is that like a customized code that you have to do yourself, or is there some easy type of library for that, like PCA?
Yeah, I'm pretty sure there should be code for it.
I linked the implementation of UMAP that I've used in the past, and UMAP is actually, it depends on exactly what you're doing, but I would say, for me at least, I prefer UMAP over t-SNE at this point, partially because it's just a lot faster. t-SNE is apparently not very quick to compute, and UMAP is much faster as you scale your data. So I use that a lot. Can I share screen for a second? I actually have an example of something I can show.
Can you help me? I minimized it and then I can't find it anymore. Yeah,
That's fine. I can do it for you. One sec,
okay,
guys.
thanks, Ted.
think I can do it.
I think I stole it. Can you
Were
guys
you
see
successful?
my screen now?
Yeah.
You guys can see it?
Yep.
Okay. So this was a project I did where basically we scraped a whole bunch of answers off of this website that has a whole bunch of questions and answers where basically, I'm trying to think of what it was called. There was some website, but basically people are able to ask medical questions on this website. And then a whole slew of verified doctors are able to just answer the questions. And so you can have this sort of discussion thread where someone will say, basically, I have this, this, and this, and then doctors are able to just respond and they can have a discussion there. And we did this project where basically we wanted to map their questions to existing answers, because a lot of people are going to end up asking the same question. So we wanted some sort of search to say, you're asking about this, let's map it to something that we believe is similar. So what we did is we passed the text of the questions and the answers to BERT, and BERT outputs some embedding. It's 512 dimensions long, or different depending on how you lay it out. But basically, that does 512 dimensions. And then if you want to actually visualize it, we can't see in 512 dimensions. So you have to map it down to something lower. So it's kind of like one of the examples that we saw in the book where they're reducing it down so you can actually visualize it on a 2D or 3D plot. And so this is a 3D plot that I made with Plotly. If anyone hasn't done these before, they're pretty easy and pretty fun. It builds a whole bunch of stuff in there for you. So basically what we're visualizing here is this is their source question. So someone enters in a question and then we want to return potentially other similar questions and also answers that might map to the same thing. And so just visualizing it, the blue dot is the question, and then the orange is all of the other similar questions. I did the 500 that are closest or something like that. And then the green are the similar answers. The red are the dissimilar questions. The purple are the dissimilar answers. And you can see that there's certain points that are close. And like this one is talking about incomplete right bundle branch block, certain HDL value. And then if you go one over, you can see, oh, this is also asking about cholesterol values and triglycerides and similar vocabulary. So you can see that it's actually doing a good job of clustering those together and saying these are all kind of on similar topics. And you wouldn't be able to do that if you were just trying to look at it across 500 dimensions or whatever else. But the other thing you can derive out of this is you can see these clumps and you can say, okay, what is common in this whole grouping? And in general, I don't think there's actually much in common. I think this is kind of just an artifact. But in general, you can sort of look at these and then evaluate the text a bit more easily. And one of the nice things about Plotly is you can turn things on and off. So I can turn off answers and questions and etc. So I just wanted to plug that because this is one application of this. And if you ever want to visualize this stuff, Plotly is a good way to do that.
Has anybody ever come across a case where they want to like dimensionally reduce whatever a space, but they like, you want to weight certain features more in that dimensionality reduction, which you know like beforehand, like what you want to weight more, and like how, yeah. Have anybody like come across a case like that?
I could see that being valuable. I've never really had to do that. I just opened the UMAP thing and I saw that there was some like supervised dimension reduction and stuff like that. So I would assume that UMAP has some sort of capability on that. But I haven't personally done that.
Okay. I mean, like I've So I'm like a bioinformatician, so I kind of work with different like sequencing data sets, and there's like a lot of work that goes into like, there's like these different like sequencing methods, and people like kind of try to like integrate like these different sequencing data sets, and the way they usually do this is they try to like put them in like the same like feature space, and that's usually some dimensionality reduced feature space. And I guess like there was like a problem that I was working on where I wanted certain features to be weighted more, and I guess it wasn't like necessarily UMAP, it's like some other like feature reduced space. And the way I just ended up doing it was just scaling those features like based on particular weights before running PCA on it, and then running I guess in the case of like UMAP, you would then like construct the nearest neighbors graph and then run UMAP on the graph.
Yeah.
So I don't know if like that was how I ended up doing it, but I don't know if there was like.
I'm not sure about UMAP, but for PCA, if you just scale everything to unit variance, right?
Yeah.
And then you multiply column 1 by 3, you will be triple weighting it in PCA.
Yeah. I mean, yeah, that's like sort of what I ended up doing. So I don't know. It made sense to me. I guess it makes sense to other people. So
yeah, I know the theory, but I haven't actually run across that at work where I was weighting. I was manually putting my thumb on the scale and saying, weigh this column more than the other ones, you know?
Right.
Can I please show very, very simple case of PCA, because it was my understanding that since in books they never actually showed the formula for components, and they only describe it. And you know, not everybody good with description. Some people want to see a formula. So can I please show it?
Sure.
Okay. Okay, so it is PCA applied to a very simple data set, vine data set from here. And we have a particular columns with values, with some properties of these vines. And we are supposed, I guess, to guess their, I think it was the quality, oh well. Okay, and I'm sorry, it is a very old script which was used, and I just try to put it in quickly so it will be visible. So we download the data set. We have our output variable, and we do the usual splitting, scaling, and then we apply PCA. So then we can, I guess I can drop this because it is a classifier, and I don't want to talk about classifier. But what are the components? We can do a data frame which shows them. These are our components, which are coefficients for particular values. So the first component is this coefficient multiplied by the amount of alcohol. Then we have minus this coefficient multiplied by the number for malic acid. Then we have this coefficient, which is multiplied for the amount of ash. And I need to add that since we scale it everything, then here we actually mean scaled values. But the idea is that this linear combination about which we talked, it looked like this. And
yeah, so in this case, Maya, since they're scaled, you can say that principal component 1 is mostly flavonoids, that's the 0.42, and then total phenols 0.38, and there's a whatever that is, OD 280.37. So
Well,
those are the
but
three
this
things that
difference is
most
not- yes.
contribute to PC1.
Yes, I wanted to say that, yes, we may choose the biggest coefficient and to say that it has the biggest input. But the thing is that this value is not very different from this one, that this whole thing is pretty much, if you change splitting, then it can change hundreds values. So it's not very reliable.
Yeah, but I'm just saying as sort of interpretability of the principal components, right? The PC1, the direction of maximum variance, is contributed most by those three things: flavonoids, total phenol, and OD 280. Whereas the second principal component, you can say the biggest contributors are color intensity and alcohol, right? So I think that's the benefit of you showing the exact weightings that went into those principal components.
Yes, but you know, it could be not, the difference between coefficients could be very small. So in this case, we cannot actually say what is more important, what is not. And this is why interpretability with PCA is so difficult. Okay.
All right, thanks, Maya. So there's a question in the chat. How do you know that the components are orthogonal? I don't know how to answer that other than to say that the algorithm itself always produces orthogonal components, orthogonal eigenvectors. So they are. I don't know if anybody has a better answer.
By design, Ted, by design.
Yeah, pretty much so.
Yeah, you as a user don't need to worry about it. They are by design orthogonal.
Yeah. You know, if somebody really cares, I guess you could, everything's open source. So you could read the sources if you wanted to, but by design, it is designed to force orthogonality, is that a word? Into the outputs.
Yeah, if you do singular value decomposition, if you get all the eigenvectors, then they are orthogonal. It just
Which is another restriction of PCA. It could be that there could be beta vectors which are not orthogonal, but you cannot get them.
Yeah, I think the book might have even mentioned, just in one sentence, another algorithm that produces a span that is not orthogonal vectors. It's still the same number of dimensions, but they're not required to be orthogonal. I think there's just like one sentence somewhere in the chapter.
So I have a question.
PCA as your first principal component plus the PCA of everything that's left. And once you've gotten rid of that first principal component, everything that's left has to be orthogonal to it. Otherwise, it'd be in that principal component.
That's a good explanation. But mathematically, the way people compute it, they don't have to compute them one at a time. They can compute them all at once.
Can I ask a question about PCA for compression? On page 224, it talks about, I understand we compress it, gives us, you know, fewer features that we have to consider, but then it talks about decompressing it, and I don't understand why would we decompress it after compressing it?
I don't know. I don't remember exactly what it said in the book, but basically the whole thing is if you compress it, you do want to be able to obviously restore the original data, right? So the compressed data is in a different set of dimensions, a different set of axes. So you can't, for example, if it's an image, you can't look at it. You have to actually put it back to its original, whatever it is, 64 by 64 representation in order to look at it. So once you compress something, you do want to be able to decompress it to get back to your original. But in this case, it's not your original, it's your approximate original.
I think that's the point that he's trying to make right there, is that even after you go through all this, you know, compress it and everything using with PCA, if you uncompress it back up, you can still say a zero, this is MNIST, A 0 is a 0, 1's a 1's, a 2's a 2's, a 3's a 3's. They look similar.
Yeah, you're trying to recover the approximate original.
Yeah, it's sort of like, you know, if you zip a file, right, you want all the bits to show up. Well, that's probably a little bit, but if you do a lossly type compression in a photo, you still want the dog to look like a dog. It may just not look as, you may not be able to count all the hairs on its head or something like that.
Yeah, I mean, anytime you have a JPEG file, it is no longer 64 by 64. It's been squished down. And so you have to actually decompress it to recover the original representation as a rectangle.
Yeah, but even there, JPEG is lost. So you don't get the original one back, right?
No, that's what I'm saying. So PCA would be not as good as JPEG because a lot of man hours went into inventing JPEG, but it would do the same kind of thing. You could store your images in fewer bytes on your drive.
Yep.
But you'd still be able to reverse it. With PCA, it is reversible, and you'd be able to reverse it. You'd be able to recover your uncompressed approximate original images.
Okay, thank you.
So I had a question for Ryan. Oh, he bailed on us, didn't he?
Harold ran out of battery. Ryan's still with us.
Oh, Ryan. So when I looked up, I had never heard of some of these techniques, namely, let me see here. Yeah, I'd never heard of UMAP, and I kind of went up to somebody who did a comparison of UMAP and TSNE, and one of the things they pointed out is that you get better separation from your various classes, if you will. Of course, they're using MNIST, so you know the difference. Things cluster together like shirts and there's a t-shirt and a shirt in MNIST, and those cluster together, but you get more spread, let's say, between t-shirt and shirt from dress or sandal or something like that. Did you experience that with your data?
I haven't really focused too much on the sort of underlying classes after. So I haven't looked at that in too much detail, but I will say that TSNE is very focused on the local data points. It's not very focused on the global pattern. UMAP captures more of the global pattern. TSNE basically looks at like, here's the 10 closest points, and then it tries to do some kind of clumping of them. And UMAP looks a bit more globally than that. But yeah, I haven't looked in reference to the targets necessarily. Like in that previous project, we didn't have a target necessarily. We don't even know what the closest question is. We just want to make them occur in similar places, and we had to do some trickery to try to make that work. But we don't necessarily have labels saying this is the closest answer to that question or anything like that. So it's kind of hard to say. I didn't look at that too closely.
Okay, thanks.
Yeah, I think Ian mentioned when we were talking about chapter 2, this is more related to the modeling side of things, but that there's no way a priori to know which algorithm is better. You know, you can't just know, right? So I've seen the same thing. Ryan, I wish I had your recall for like different websites and papers and stuff. So I can't remember where I read it, but somebody was doing dimensionality reduction, and they commented specifically on certain algorithms look more at the global structure, and certain algorithms look more at the local structure, and they had an intuition. Okay, they weren't sure, but their guess was that they cared about global structure more for their particular problem. So then they, you know, tried UMAP before they tried TSNE, but they still tried TSNE. You know, if it worked, they would have been happy to use it. But so you can have some intuition as to which one will work. If you think it's linear, then PCA might work really great. But I would say that at the end of the day, unless the algorithm just takes forever to run, you usually try the different ones. Like I've seen a bunch of papers where they say, here's 5 different, you know, visualizations using different algorithms just because they didn't know. They just tried them all.
That's when I do this very often. the visualization doesn't do anything for you, really. It can maybe be a sanity check and say, like, am I actually clumping these things together in a reasonable way? But for the most part, it's kind of just a showpiece, just to be like, hey, look, these things end up similar, and you can show that to someone and they go, wow, cool. But when I do that every time, I'm probing and I'm trying to find the hyperparameters and which algorithm and whatever else gives me the most reasonable thing. So on that specific one, the one that I already showed, I tried t-SNE, I tried UMAP, I tried truncated SVD, I tried them with various different perplexities. I actually had a notebook where I just iterated through a bunch of different hyperparameters until I got ones that looked reasonable, because some of them just turned out looking like complete garbage. I mean, I'm a bit cynical on most of the unsupervised and sort of clustering stuff and dimensionality reduction. There was a paper a while ago that was like reading the tea leaves or something like that. And it was kind of showing that people are going to do clustering and dimensionality reduction and whatever else, and they're always going to derive some meaning out of it, because they always just like, you look at it and you try to make sense of it, but it doesn't necessarily mean that you've truly extracted something of value or proven anything. But yeah, I dropped a link. I don't know if that was necessarily the one. I'm gonna look for a different link. I don't think that's the one I was initially thinking of, but there is one that talks about dimensionality reduction on what's it called? How to use t-SNE effectively. That's one. Maybe I can share a screen for this too. So this is another Distill. They have some amazing visualizations. I looking at these. And so this is kind of like in the chapter, we looked at the Swiss roll example. This is showing with t-SNE how it converges and how it clumps things up, different data sets. And this is kind of showing what Jerry was asking about. Like if you actually look at the underlying labels, you can see how it ends up splitting them in various different ways. But they talk about you change the hyperparameters, you get wildly different results. So for example, this is the source data, and then you can do t-SNE with various different perplexities, and you can end up with something entirely different. So if you do it with perplexity 30, you get these nice tight clumps. And if you do it with perplexity 100, it's just complete random noise. And that's kind of been my experience as well, is you kind of have to just manipulate it until you get something you like, which is not particularly scientific, but that's just how it works. So like with this, it converges down all the way to a single point, which is kind of absurd.
Or it's perfect clustering, depending on your perspective.
Yeah. But this I would say is worth a read if you're interested in t-SNE.
This is really cool. How do you remember these websites, or do you just have to Google and find them?
Well, Distill is something I've read quite a bit.
Yeah,
but
yeah. They do have the most beautiful articles.
Yeah, they always have very interesting things. Was that the one that you were thinking of, though?
Me?
Yeah, you were saying that you
no, Ryan. I put a link to the one that I was thinking about.
Okay.
And I was comparing UMAP and t-SNE, right? Right.
Yeah.
That's cool.
Yeah. Just to see, I was just curious because I'd never heard of UMAP before, and when I went to look at it, it looked, at least in that picture, it looked good. I didn't know what the reality was. So.
Yeah, but I think as intuition, right? You can imagine whether or not you're saying, like Ryan was saying, what are the points closest to me? And so you could just go marching off kind of in the wrong direction, right? versus if you look more globally, you say, hey, big picture, you know, some things are over here, some things are over there. Let's start, you know. I think that's kind of a good way to think about potential differences in the results you might get, depending on the kind of data that you're trying to squish down. I mean, you know, when you have 500 dimensional data, 2 dimensions is really so few to try and express what's going on.
Unless they're the right 2, Ted.
Yeah, like those 2 dots that Ryan had. All right, so we're at 1:30. I think what we'll do is we'll call it a wrap for the book club, and we'll transition now to the project collaboration time. So thanks for everyone joining us. We will be back same time next week. Kalika's going to talk about clustering. So actually fits very well with what we were just kind of talking about, since a lot of this dimension visualization is when we're doing clustering. And so if you're not staying for this part, you're welcome to drop. We're using the same Zoom. And so this is where we have sort of open office hours, can ask anything. I have something, it's actually PCA related, that the timing worked out well. I can share that if people don't have questions, but basically how this works if you're new is we just open the floor and people can either show us code, a problem that they're having, or ask a question about how something works, or they're trying to figure out how to formulate a problem, or just whatever.